Good evening, colleagues. My name is Joseph Yohanga. Together with my colleague, Lyndon Baraka, we are here to present TSC model agnostic models for malaria prediction. We are focusing on federated features, continuous learning for medical image processing with federated feature augmentation. Here we will pardon me a bit if some words are not clear because I have an issue with my tongues. It has some words, so sometimes I may struggle to pronounce some words. For today, kindly bear with me. So I will move straight away to the problem statement. Traditional machine learning methodologies are inherently dependent on extensive and centrally collected data. So this dependence creates significant privacy risk as sensitive data from different hospitals must be upgraded to the central repository. So this raises a previous concern and other governance concerns. So federated learning addresses these issues by allowing distributed systems such as health institutions across the country to collaboratively train a machine learning model without sharing sensitive local data. So where the local health clinics are training their data, they always send model updates to the central server, and the local data remains on the local device. However, this approach also introduces its own challenges, which includes non-independent and identically distributed data. This negatively impacts the convergence and the performance of models, which are trained via federated learning techniques. So, in addition to that, hospitals do possess limited number data sets due to high costs of annotation and limited expertise and logistical barrier within the rural areas. So this is why we are going to apply feature learning. This is a technique that enables you to train the model using limited number of data samples while achieving high level accuracy. So traditional federated models also suffer from catastrophic forgetting, whereby model will lose the previous knowledge learned upon receiving the new data. So we shall overcome this by using what we shall employ, what we call continuous learning. So continuous learning enables model to adapt to the new data without forgetting previously learned knowledge. So our objectives we are to design a previously preserving federated learning framework for malaria image analysis, which are integrate feature learning methods that allow rapid local adaptation with minimal number samples. We shall also implement continuous learning for real time updates without losing the previous knowledge acquired. So the novel to our solution, we are integrating federated feature learning with continuous learning and feature augmentation. So we are also eliminating the need for central server, eliminating the need for central data collections while complying with highest data regulation. We are also applying incremental adaptations, whereby the model is able to adapt to the new data without forgetting the previous knowledge. So this is the brief overview of our system architecture. So each here clients, these can be local hospitals. We train models from their local devices. Then they will send the updates, only the update to the central server. The central server aggregates the matrices received from each of these clients, then sends back the global model to each of these clients. So the clients instead they will use a global rich model to do their prediction. In summary, that is the overview of the architecture. Then this is the proposed model for malaria detection. See, this is the local hospitals. This is the federated learning. This local hospital we train and send the matrices to the server. The server does the aggregation, then sends back the global model. So this model, we are optimizing it and deploying it to the edge devices. So these edge devices are used by the local clinics to do the detection. So the matrices, the performance they get is sent back to the model for further fine tuning, and so the process is continuous. So the data set we used was Sequoia. This was obtained from National Institutes of Health, and this data is labeled, indicating whether the image is affected or not affected. So also digitizing of the images to the uniform size of 128 by 128, shuffling also did run random rearrangement of images and normalizing of pixel value by dividing each pixel value by 255 to obtain a value between 0 and 1. The above techniques are very important to ensure that the model will not be able to overfit. So also do that augmentation. This involves rotation, flipping, and slight brightening variation. This is to create more variation of the images. So we also split our data into train, validation, and test split. And then also do the EDA. From this, you can see that the affected images, their texture is a bit irregular, so this makes it easier for clinicians to be able to know which cells is affected or not affected. So from the training, this is the performance of the model across 10 rounds. So in each round, the server does record the performance. So here you can see that the ace rounds obtain the highest precision. So since precision is the most, it's what is most taken care of within the medical setting. So here our checkpoint was on around 8. So we also did explainable AI using WordCamp, whereby it indicates the regions that the model based on to make the predictions. We also use the line which highlights the parts of the images that were deemed important during the prediction. What is the relevance, impact and relevance? The impact and relevance, malaria is prevalent in Uganda, so any approach that is geared towards eliminating it will be very much welcomed. Uh, then Uganda as a country, it has got a poor infrastructure. Poor infrastructure in forms of trained personnel. So basically in rural areas, there are no trained personnel. So by putting in place a system that is able to, that will aid the locals within the rural areas to detect malaria within the shortest time possible, it will be of relevance to the community. So the solution also help preserve privacy through federated learning. So malaria is also a global challenge. So any effort that is geared towards eliminating or reducing it will be of a great impact to the society. And then our solution also align to SDG 3, 10, and 16. Our target users and beneficiaries will both healthcare providers, patients, and pharmaceutical companies. The intellectual property and innovation, we are providing a previously serving federated learning framework that integrates future learning and future augmentation plus continuous learning. For monetization, we are providing malaria detection as an API that healthcare and researchers will integrate into the existing system without needing to train a model themselves. So this will be offered on demand where users can only pay for the computation they run. Then future works, we intended to do extensive field trials across multiple Uganda health centers to validate the system and the real world conditions. So that is all from us. We welcome questions.